So, just finished up a polytropic example. By the way, it would not be hard at all on that previous example then to figure out what is the heat lost by that system. In fact, that'd be a nice little exercise if you want to do that on your own time. Normally we don't have class time, and I don't want to take too much of your time. I need you to use it as you like, but that really would be a pretty easy problem now that the boundary work has been found. That's kind of the hard part. You know, and just to mention quickly here, that I know that's a lot of work to get to an answer if you look at that problem, but think about this. If I know, if they tell me it's polytropic and they give me the n value, I don't have to do all this algebra here. Right? And a lot of times they will. A lot of times they'll give you the n value. So if they give me n, if they give me the n value, and or if they give me the c value, because I had to do algebra to get the c value also, right? I do additional algebra to get the c value, which none of it's hard. It's just time. But if the problem had right up front given me the n and the c values, this problem's actually pretty easy, right? Because if they've given me the n and the c values, then this is all it breaks down to. Boundary work is this. By the way, there is a pre-derived equation in your book you're welcome to use if you understand the rules associated with it, that if you're allergic to calculus, and you don't want to have to do, Steve, that calculus stuff scares me. I'm not going to do it. I'm just going to use the pre-done equation. Okay, then I would suggest if you've got a calculus allergy, if you have a calculus allergy, you're probably in the wrong place. But that's fine. There's a pre-derived equation. But again, notice this is real. If I know n and c, this is all the problem breaks down to. Right? Go look up properties, find the volumes, find the boundary work. Done. Okay, so don't let this problem scare you off in polytropics. They're not normally that intense. This one just was kind of the worst case scenario. And that happens sometimes. But again, if you want to go back and find the heat lost in that problem, that would be a nice little exercise to do. Okay? If you want to sketch that up and email that to me, and we can talk about how you did. I'm fine with that. Okay. All right, so if we go back and look, again, Chapter 4, our whole focus here is first law for closed stationary systems. And if we look at that expression from last lecture, again, we've talked about heat and work a little bit. A lot of times the first law is going to be one of our tools we use for one of those terms. If those are the unknowns, a lot of times we're looking for the heat maybe. Maybe we're looking for the work. Right? So we can maybe use the first law, or maybe it's electrical work. I can find voltage, current, and time. Maybe it's boundary work, and you can compute it, as we've done a couple of examples of that now. So the question becomes, what do I do with these u values? Right? And that's, if you look in the notes and what I would normally do in the classrooms, I'd have these PowerPoints, and this blank slide would come up, determining u values. And on the smart board, I would write on here, what are some ways that you would determine u values? So let's do that. I know I've said this a few times before, but what you probably want to do is be taking notes. It's probably really boring to just watch and listen to me talk about thermo for 2 hours at a time. But if you'll take notes, you'll trick your brain into actually thinking this is important, and you'll start memorizing, or not memorizing, but at least remember some of it. Determining u values, there are 3 ways. Number 1, the obvious, table properties. Right? We just spent an entire chapter 3 talking about how do you use those tables in the back of the book. And you will get good at them if you will practice at them. Practice, practice, practice. Table properties. For water in R134, I need 2 properties. Unless we know it's a liquid. If they tell me it's a liquid, that serves as a property, and then I just need to know the temperature. Need 2 properties for water in R134. For ideal gases, you do have some ideal gas tables. They will give you a u value. It is only a function of temperature. That's all I need. So you do have ideal gas tables that will give you a u value as a function of temperature. You know the temperature, you know the u values. That's the only property I would need for air or other ideal gases, at least using the tables we have in our text. The second way I could determine U values could be the first law itself. A U value is a variable within the first law equation. I can solve the first law for one unknown, because it's one equation I could solve for one unknown. So if I know all of the energy crossing the boundary, I know the mass, and I know one of the U values, the other U value becomes the only unknown. And that happens sometimes. Like the problem might ask for what's the final temperature of the water. Well, if you solve for the final U value, you can probably use the U value in conjunction with the pressure or something like that. So I could use a U value in conjunction with the pressure to find a temperature or something like that. Okay? So you could use the first law to solve for any unknown within the first law, and if a U value is the only unknown, that is a second way you can determine U values. The third way you can determine U values is a quantity we call the specific heats, or the specific heat capacity, the specific heat carrying capacity. Right, now, the hope is, again, you should have already had a chemistry class before you get here, some kind of chemistry class, and you probably talked about specific heats there. And the specific heat is the energy required to raise the temperature of a unit of mass of a substance by 1 degree. It is entirely dependent on the substance being heated. Okay? Also dependent on the phase. And so these are important things. This is a definition directly from the Chamberlain-Bowles text, but again, it's important to understand that it's dependent on the substance and also dependent on the phase. Liquid water has a much higher specific heat capacity than steam. Water vapor does. The molecules are more closely packed together in the liquid form, and therefore it takes more energy to raise those molecules' temperature to get them at a higher state. Okay. Now, you will have quantities we call C sub P and C sub V if we're dealing with substances that can expand or contract. From your chemistry class, if I'm teaching a chemistry class where I've got people that don't have a lot, they're not very mathematically mature, they're not very far along in their math classes, and we need to oversimplify everything for them, and that's okay, through no fault of their own, that's just where they are in their progression. Then I would tell you C sub P represents the specific heat at constant pressure, and what I would tell you for our purposes is that doesn't work. Right? We don't have to have constant pressure to use C sub P. We don't have to have constant volume to use C sub V. In fact, there will be a lot of times we will not have constant pressure or constant volume, and we will use these quantities. That is not a limitation for us because we understand calculus, and we have a basic understanding of calculus and an advanced understanding of algebra, so we can be a little more straightforward with you and tell you C sub P relates enthalpy. So C sub P relates enthalpy. C sub V relates internal energy, the U value, enthalpy being the H value. So C sub P will allow us to determine H values. C sub P determines H values. C sub V will allow us to determine U values, or changes in U values. Okay? Now, C sub P is going to be larger than C sub V. Why? Well, if we do look back here at these things I've just crossed out and said, well, C sub P in a oversimplified scenario represents the specific heat at constant pressure. So if we do assume the pressure is constant, right? If we assume the pressure is constant and I heat a substance up, right? So if I have some kind of fire down here providing heat into this cylinder, right? So some kind of heat source providing heat into the cylinder. If I heat this cylinder up and the pressure is constant, if the pressure is constant, right? If the pressure is constant, that means something's going to happen. If I heat the cylinder up, what happens to the air inside? Well, if it can, it will expand, right? So as I heat this up, that cylinder will expand. That expansion, as we've already found, means that there's a boundary work process. And that boundary work is additional energy that goes out of the system. So if I put heat into this thing and it's expanding, meaning it's got boundary work, it's got energy coming out, that means I have to put more heat into it to account for this boundary work that's going out, right? So whereas if I'm dealing with a constant volume scenario where the system can't expand, there's no boundary work that heat has to account for, so I don't have to put as much heat in. So C sub P will always account for this additional boundary work heat if the system is allowed to expand, or at least that's why it's larger than C sub P. Okay? So work, again, if I have boundary work, that means work is going from the system to the surroundings. The system is expanding into the surroundings. It has to push the surroundings out of its way, so that there's additional energy required to compensate for this work out term. Okay? Now, as I mentioned earlier, and these are partials, meaning there's going to be more than one variable at play, or potentially more than one variable at play. Okay, so C sub V is going to relate a change in internal energy with respect to temperature. And C sub P is going to relate a change in enthalpy with respect to temperature. Again, by definition of a specific heat is the amount of energy required to change the temperature of a substance. If I go to the differential level and say, well, let's look at a differential amount of energy, tiny little slice of energy, which represents a tiny little change, differential slice change in temperature. And again, maybe it's more than one variable, it's probably more than one variable, so we'll use partials or inexact differentials here. Right? These are partial derivatives, U and H are dependent on more than just temperature, and we know that's true for water in R134, so using it for big property tables, you have phase, you have other parameters, other variables at play. However, what we do know, again, based on this expression here, delta T, C sub V is equal to delta U, and we go to the differential level, right? And we do know through science that ideal gases, temperature is the only thing that controls a U or an H value for an ideal gas. So I can use a regular ordinary differential, regular D there on those parameters. Okay. I got to start my timer. Yeah, I've got a little bit of time. So what that means is if I integrate both sides of this equation from state 1 to 2, so if I integrate here, integral du, it just gives me delta U. Integral C sub V dt, well, that's just this quantity here. So I need to be able to integrate C sub V or C sub P as a function of temperature to approximate a change in internal energy and a change in enthalpy. So that means I need C sub P and C sub V as functions of temperature. Just like with boundary work, I needed pressure as a function of volume. Here I need these guys as functions of temperature. Now, if you go in your text, and I don't know in the current edition of the text, this is probably from like the 8th or 7th edition, that page number, but if you look in your text on table A2, you will find that C sub P and C sub V values do not change a huge amount as a function of temperature. Maybe they're going to change less than 10%. So two significant figures are, one significant figure is always correct, one significant figure does not ever change, and very rarely is this the second significant figure change. The only thing that's going to change for C sub P and C sub V as you change temperature is going to be the third, fourth, maybe and the fifth significant figure. So not a huge change in specific heat as temperature changes, especially over a small temperature change. So what we normally do is we normally assume a constant specific heat within our operating range. Now there is, within your text, they're typically going to give you the coefficients for a third order polynomial, right? So again, you can have C sub P or C sub V as a function of temperature, and it's going to be a third order polynomial, and you could actually do the integral. Normally what we're going to do is we're just going to say, yeah, we're just going to assume that it's constant. I gotta quit.